So chapter 8 about roots and radicals starts on page 567, and we're gonna go directly to section 8.1, which is just about finding roots. Finding roots. We're gonna focus only in two kinds of roots. We're gonna focus on square roots and cube roots. So let me start with an example. The thing that we're going to learn here is just simplifying, how to simplify or how to evaluate radicals. So we're going to have this symbol. This is the radical sign. Anything that goes inside is going to be the radicand. And usually this area here, this place is for the index. So there is a number and usually an integer that goes here, a small number, and we call that the index. And sometimes when we are taking square roots, so the index is 2, and usually we don't write the index. So anytime that you see just this radical, you should understand that this is a square root, so there is no index there. So we're gonna start evaluating radicals. So we're gonna do evaluation of radicals, and the only steps that we're gonna follow is just you're gonna rewrite perfect squares as a quantity, and you're gonna use this notation. So, and you're gonna rewrite in other cases perfect cubes as a quantity raised to the third power. Then the next thing is that you're gonna cancel radicals and exponents of the same order or index. So for example, so let's see, we have example 1 on page 569, and in that example we're going to evaluate first the square root of 64. So and these are the steps that we're going to follow in any case, whether you have a number here or later we're going to have algebraic expressions. So that's the reason this is the method that we're going to follow. You might know now how to get the square root of 64 and say, oh, it's 8. But these are the steps. So first, we're going to rewrite the number as a perfect square. So 64, you know that 64 can be written as 8 squared. And then we have the radical here. So you can have it in this way. You can have it, as I mentioned before, by using a parenthesis. So both ways work for us. So the point is that once you have a perfect square in the radicand, then you can cancel the radical and the exponent at the same time. So what I'm going to do is that I'm going to cross this radical, indicating I'm going to remove it, and I'm going to circle this exponent to indicate that I'm going to remove it too. So at the end, you end up only with 8. So that's the answer for this first example. So let's work on more examples. So this is the procedure that you're going to follow. You're going to rewrite expressions as perfect squares or as perfect cubes, and then you're going to be able to cancel radicals. So the next part of the example is negative the square root of 49. So again, you just need to check, is this a perfect square? Oh yeah, it is a perfect square because I can write 49 as 7 square, and then I need to write the radical sign and the negative sign that is outside. So you can see here that you can cancel again the radical, because this radical is of index 2. Remember, sometimes we don't write this, sometimes you can write that just for you to remember. So we are removing the radical and we are removing the exponent at the same time. So this is very important because most of the mistakes I've seen students made in the past is that they get this result and they still or they continue writing the radical sign. So that's not the right answer. So the right answer in this case is 7 without any other uh, radical here. So that's part B. We have part C is just the square root of 1 over 4. So we can just break this fraction. We can distribute the radical sign, in other words, in the following way. You can just take the square root of 1 and the square root of 4. That's one way. And then you rewrite the radicands as perfect squares. So 1 is going to be 1 square. We still have the radical here, the radical sign. And 4 is 2 square, and then we have the radical sign. So in this case, again, you can just remove the radical sign and the exponent, the radical sign and the other exponent. So you end up with 1 over 2. So that's this exercise. Then the last one. Oh, there are two more. So we have now the square root of 9 plus 16. So this exercise is very important to emphasize the importance of the plus sign. So remember, the plus sign and the minus sign, they are operators that are very important, and they put or they hold quantities together. So you cannot break this quantity. You cannot break this into radicals, like for example, square root of 9 plus square root of 16, because these two quantities should be treated in the same way that we treated before. For example, x plus 6 over x minus 9. If you remember, we cannot eliminate, we cannot remove this x and this x, only because remember, this x is part of this entire unit, and this x is also part of this entire unit, so you cannot break. So these quantities, these expressions are unbreakable. So the plus sign again, or the minus, they are a very important part in the expression. They hold many things together, so you cannot just break it in a simple way. So you cannot remove excess the x here. The same way we cannot break this into pieces to get something like, for example, square root of 9 plus square root of 16. So this is wrong. So the best way to prevent these mistakes is as we did before. So we enclose in parentheses the quantities, and then you know that this is a unit, so you cannot break this unit. So what we're gonna do is we're gonna see whether we can combine terms inside of the parentheses, if we can simplify the quantities inside of the parentheses, and then we're gonna see whether we can continue on and trying to simplify the radical. So in this case, yeah, we can add 9 and 16, so you're gonna get the square root of 25. Now 25, is 25 a perfect square? Yeah, that's a perfect square, because you can write 25 as 5 square, and don't forget we have a radical sign here. So you can cancel now the radical sign and the exponent at the same time. So don't forget that. If you do it in a different order, or You leave one step after the other. Sometimes we make mistakes and we forget finishing our work. So in this case, the answer is just 5. So now the last part of this problem is now is the square root of 9 plus the square root of 16. So you can see now that you have two radicals. So I'm going to emphasize here that the entire expression, this expression is a radical. That's the way that we refer to this expression. And this is another radical again. And if you have only the symbol, this is a radical sign. If you have the part that is inside is a radicand, and again, the number that goes here is the index of the radical. So in this case, we have two radicals. So we're going to treat both radicals independently, and at the end, we're going to combine them with this plus that is here. So you can rewrite 9 as 3 squared, and then you have the radical sign here. Then you have this plus, and then you're going to write 16 as 4 squared, and then you have your radical sign. So now you have two radicals, so you're going to eliminate or cancel the ones that you can. So in this case, you can cancel this and this. And remember, you need an exponent here. You need exponent 2 to cancel this radical. You need this exponent here to be able to cancel this radical. So at the end, you're going to write what is left. And what is left from the first part is just the number 3, then my plus, and what is left from the last part is 4. So you're going to get 7 as the final answer. And checking just problem B, I forgot something. Once you remove everything here, there is still a sign here that we need to keep, okay? Because this sign is outside of the radical, it's not part of the radical. This negative sign was here since the very beginning, so be careful. The only thing I'm going to just say is that if you have, I'm going to write an extra exercise that is not here but is important. So if you have, for example, like here you have b negative the square root of 49. Let's say that you have the negative side inside. So instead of outside, we have the negative here, and then 49. So in the case of radicals of this type, square roots. So when you have square roots, so the radicand should be positive always. The radicand should be positive to be able to remove the radical sign. So in this case, you know that you can write 49 as a perfect square, so you can write just 7 squared. But the radicand is negative, so we cannot remove this sign and this exponent because there is a negative sign inside. So you cannot cancel the radical sign and the exponent because the radicand is negative. So we need a radicand that is positive, strictly positive, to be able. So in other words, we don't need anything between the radical and this parenthesis, nothing, just the parenthesis next to the radical sign. So if you have a negative sign, that's a bad sign. This is going to be different when you are taking the cubic root, okay? But this is going to be the next part that we're going to work on. So now you have a lot of different cases. So it's your turn now to work a lot of problems because this section is very important to get expertise that we need to be able to work with radicals. A lot of radicals that we're going to have radical equations and operations with radicals. So we're going to work now 8.1 exercise set And this exercise set is on page 574. So you're gonna simplify, or you're gonna evaluate. We're gonna evaluate the following expressions. So we have a lot of expressions that you're gonna work on. So number 2, square root of 16. Number 4, negative the square root of 16. Number 6, the square root of negative 16. Then we have 8 is gonna be the square root of 1 over 49. Then we have 10 is gonna be the square root of 1 over 89. And the number 12 is gonna be negative the square root of 1 over 121. So you're gonna work these 6 exercises, and you're gonna show me your answers by using the chat box, or if you do it after the class, then you're gonna send me your screenshots by using the classwork submit button. So I'm going to give you time to do these exercises. So now we're gonna solve an example where we're gonna find cube roots, and we're gonna follow the same procedure. So we have example 5 on page 573, and we have 3 problems. So we're gonna find the cube roots. So the first one, we have the cube root of 27. So now you can see here that we have a radicand, we have the radical sign, and now we have the index. The index is 3, so that's the reason this is a cube root. So when you have index 3, then you need to find perfect cubes. So if you have perfect cubes, then you just rewrite the radicand as a perfect cube. So you're gonna rewrite the radicand as a perfect cube. In this case, my radicand is 27. Is 27 a perfect cube? Let's see. There should be a number that if you raise to the third power, you're gonna get 27, and that number is 3. Because if you multiply 3 times 3 times 3, this is gonna be 27, and you can write 3 times 3 times 3 as 3 to the cube. So that's the reason this 27 is gonna be written now as 3 to the third power, and then we have my radical sign with index 3. So now we're gonna be able to remove the radical, in this case of index 3, if you have the exponent 3 here. So these things go away, so the final answer is just gonna be 3. Okay, so let's work on two more problems. So we have now the cube root of negative 1. So the rule with negative radicands, so when the radical index is odd, you can take the negative sign of the radicand outside of the radical sign of the radical. So in other words, I can move this negative sign here to outside. So I'm going to write negative the cube root of only 1, because now the negative sign is outside. You can do this only with radicals where the index is odd, for example 3 or 5 or 7. If the index is even, like 2, 4, 6, 8 and so on, then the answer is not a real number, as I mentioned before, not a real number. So let's see. So now we have we need to rewrite the radicand as a perfect cube, and 1 is also written as 1 to the third power, because 1 times 1 times 1 is still 1. And this is the cube root, and then we have the negative sign here. So now I have a radical sign whose index is the same as the exponent that I have here. So I have a perfect cube and I have a cube root, so I can cancel both. So and I end up with 1, but don't forget the negative sign because I forgot that before. So it was a mistake. So that's the solution for this part B. So now let's work one more example. So now we have part C is just the cube root of 1 over 8. So now 1 over 8, we're going to need to rewrite the numerator and the denominator as perfect cubes. So we can do this under the same radical, or we can split this in two radicals, one for the numerator and one for the denominator. That's what I did before. Now I'm going to do it just in a different way. I'm going to leave the radical sign there. I'm just going to rewrite every piece here as a perfect cube. So the first one, 1 is going to be 1 to the cube, and 8 is going to be 2 to the cube. And now you can combine these two quantities with the same exponent under or with a parenthesis. So I can write 1 over 2 both to the cube, because both are to the raised to the third power. So that's the other way that you can do this problem. So you either go in this way without touching the radical sign until the end, when you can just now remove the exponent and the radical, and then you just end up with 1 over 2. Or the other way is you can just split the radical sign into parts, one for the numerator, the other one for the denominator, but don't forget the indexes. And then you just continue doing the same thing. We want to write 1 as 1 to the third power, then I have my radical sign, and I have another radical sign here, and 8 is going to be 2 to the third power, and then you just work this independently. You cancel this with this, you cancel this with this, and you end up again getting 1 over 2. So that's everything with respect to finding roots. So I'm going to give you 3 more problems, and then we're going to move on to the next section, which is going to be a very, very important section. So you're going to work with 3 more problems from 8.1 exercise set, which is on page 575. So you're gonna write, you're gonna work on 48, which is just the cube root of 27. Then we have 50, which is the cube root of negative 64. And finally 52 is negative the cube root of 27. So 3 more problems on this, and then we're going to continue with the next section. So yeah, work on this and send me your answers by using the chat box, or submitting your reports later by using the submit button in the classwork section. So when the index is even, a negative radicand cannot be simplified. You just write not a real number. When the index is odd, for example, you are getting the cube root of a negative quantity here. So let's say negative 27. or you are getting the fifth root of negative 100, or you are getting the seventh root of negative 2000. So the important thing is that you can take out the sign. So this is going to be equal to negative the cube root of 27. In this case, you take out the negative sign, so you're going to get negative the fifth root of 100. In this case, you're going to take this sign outside, so you're going to get negative the seventh root of 2000. And then you can proceed with the next steps if you have way for you to simplify this. So in the case of problem 50, this one that is here, so problem 50, cases you have a negative radicand. So the first thing that you're going to do is move this sign out of the radicand. So you're going to write negative the cube root of 64. And we could do that because this is an odd index. If this is a square root, you cannot do that. Then you just write not a real number. But in this case, this is an odd index. So, and then the next step is just the same way that we did before. We need to rewrite the radicand as a perfect cube. So in this case, you're going to see that 64 can be written as 4 to the cube. Why? Because 4 times 4 times 4 is 64. Then you have your index here, and you have this negative sign here that stays there. So, and it's going to be remaining until the end. So then, once you have a perfect cube in your radicand and an index that is the same, in this case 3, then you can cancel the exponent and the radical sign. So you end up only with the radicand and the sign that was got out. So that's the final answer for problem 50. We're gonna start another section. So, and the next section is based on this word. So we need to be able to find perfect squares, perfect cubes. So the next section is section 8.2. Section 8.2 on page 578, and this is about multiplying and dividing radicals. So we're gonna start doing some math with radicals. So let's see. For this one, for this section, we're gonna use the product rule, for square roots. Is on the same page, 578, and the rule is just if A and B represent non-negative, and this is important, non-negative real numbers, then, and we have the square root of A times the square root of B is gonna be equal to the square root of A times B, and the opposite is going to be true. If you have the square root of A times B, we're going to be able to break the radical in two pieces. One is going to be with A, and the other radical is going to be with B as its radical. So this is a very important rule, the product rule for square roots. So what we are doing here is that we are just multiplying radicals. So we have here two radicals. So we multiply those radicals to get a single radical. So when you multiply radicals, the only thing that you are doing is that you are multiplying radicands. So you are multiplying what is inside of the every radical. So that's what you see here. Other times, what we're gonna do is the opposite. So you have a quantity and you factor that quantity. So factoring, remember, is just getting factors. And then you can just break the radical into radicals, and then you get the product of those two radicals. So this is going to be very important. So sometimes to simplify radicals, we need to do these operations. We need to multiply them. And then maybe because the product is going to be a perfect square, and then we're going to be able to simplify. Sometimes it's the opposite. We need to break a number that is not a perfect square in two parts. One part is going to be a perfect square, the other part is going to be a non-perfect square. But you're going to see later with some examples. Now, the only thing that I need you to become familiar with is with this operation, multiplying two radicals, meaning that you're going to multiply the radicands and you're going to put the result under the same radical and vice versa. So let's start with example 1, which is on page 578. And we're going to use the product rule for square root, so find each product. So the first one, we have square root of 2 times square root of 5. So I have two radicals. So remember, the entire thing is a radical. So, and this is another radical. So I have the product of two radicals. So I'm going to get a single radical, and I'm going to do the product of the radicands. So I have 2 times 5. Then I simplify. I'm going to get the square root of 10. Then I'm going to ask myself, is 10 a perfect square? No, then that's the end of the story. Let's see. We have b, and b is going to be the square root of 7x times the square root of 11y. So again, I have two radicals. So I'm going to write a single radical for the result, and I'm going to multiply the radicands. This is the first one, and this is the second one. Then you're going to just do the math that you already know. So you're going to multiply these two quantities. So you're going to get 7 times 11 is just 77, and x times y is just x, y. Okay, now we have square root of 7 times square root of 7. So again, you're going to use a single radical, and you're going to multiply radicands. 7 times 7. 7 times 7 is just 49, but you know that 49 is a perfect square, so we're going to write 49 as 7 squared. And now we're going to be able to do a simplification. We're going to remove this radical sign and the exponent at the same time. So we get 7, and that's the final answer. One more. So we have the square root of 2 over 5 that multiplies the square root of 3 over 7. So we're gonna combine these radicals into a single one. The first radical is 2 over 5. The second one is 3 over 7. Then you just multiply the fractions. So 2 times 3 is going to be 6. 7 times 5 is 35. So you have the square root of 6 over 35. Now let's work by using the rule in the opposite way. So let's see. We have now we're gonna be using the product rule to simplify square roots. So now we're gonna do the opposite. Remember, we're gonna break a radical in two pieces, into radicals. So we're gonna use the product rule, but in the other way. So let's work some examples to understand this. So we have example 2 on page 579. So we're gonna simplify. So our first case is just the square root of 75. So now this is the very important part. So any radical that we're gonna break, the idea is that one of these two, for example, the first one, A, should be a perfect square, and the second one, a non-perfect square. That's the way that we're gonna break these radicals. So the idea is that we're gonna rewrite the number as the product of two numbers. One of those numbers is gonna be a perfect square, the other one is gonna be a non-perfect square. So for example, 75. 75 can be written as 25 times 3, because 3 times 25 is going to be 75. And the important thing is that one of these two numbers is a perfect square and the other one is not a perfect square. But this is the important thing. So we're going to break this now into radicals. One is going to contain the perfect square and the other radical is going to contain the non-perfect square. So now the one that we can simplify is the one that is a perfect square. So you're going to rewrite the square root of 25 as 5 squared. So I'm rewriting this as a perfect square, and I have the square root. The other one, we just copy that because we cannot do anything with a non-perfect square. Now, you can remove the radical sign and the exponent here. So you end up with 5 and then square root of 3. So you can see here that this 5 is now like the coefficient of this radical. And that's the reason the order in which we write this radical is important. I usually, this is something that I do, this is from experience. So my first radical is for perfect squares, always my first radical. My second radical is for the non-perfect square. Why? Because at the end, this is readable. So instead of having the square root of 3 times 5, which is very hard to read, you can have 5 radical 3, the answer, 5 radical 3. So let's work 2 more exercises, and then you're going to start practicing these new procedures. So we have now another part from example 2, and that's the square root of 80. So the square root of 80. So let's see. So we can write this as the first thing that occurs to me is you can break this 80 as 4 times 20, right? 4 times 20. So 4 is a perfect square, 20 is not a perfect square, but 20 can be still broken in two parts. So you can write this as 4, the first 4, and then 20 can be written as 4 times 5. So now I have here perfect squares and a non-perfect square. So I said before that I'm going to use the first radical for my perfect square. So I have 4 times 4, and the second radical for non-perfect squares. So you can see here that 4 times 4 is just 4 square, right? And the square root of 5 remains as the square root of 5. Then the final step is we can remove the radical and the exponent, and the final answer is going to be 4 times the square root of 5. So 4 radical 5. It's like the way that mathematicians say 4 radical 5. So finally, we have the last problem is the square root of 38. So in order for us to use the product rule for square roots, you need to find two factors of 38, one of those being a perfect square. So you can get factors of 38. You can just write this as maybe 2 times 19, but 2 is not a perfect square. 19 is not a perfect square either, so there is no point of doing this. So this is a non-perfect square. This is a non-perfect square. So it doesn't help doing this operation. So then this is the answer. We cannot simplify further. So we cannot simplify further. So and that's the answer for this problem. So I'm going to give you problem now, and then we're going to introduce variables. And once you have variables, then everything is going to be slightly different. So you're going to work now problems from 8.2 exercise set on page 585. So first you're going to multiply. So we have 2 is just the square root of 2 times the square root of 17. And don't forget simplifying the final radical if possible. Then we have 4 is the square root of 7x times the square root of 11y. Then we have problem 6 is square root of 10 times square root of 10. Then we have problem 8 is square root of 3 over 5 times square root of 5 over 7. Don't forget simplifying fractions if you can. Problem 10 is square root of 0.2x times the square root of 3y. Problem 12 is going to be square root of 7 times a times the square root of 1 over 7 times b. So, and finally, from this section, or from this subsection, you have 5x over 11, that's the square root of that is the first radical, times 11 over 5. So I'm going to need at least the last 4. problems. These ones, 8, 12, and 14. Solve these three and send me your answers because I need you to work a couple of more problems. So problem 16, you're gonna simplify in these cases. So you're gonna simplify. So we have the square root of 27, then the square root of 28, and finally the square root of 300. So simplify this problem. So you have a lot of problems that this were these three from the first subsection and the other three from the other subsection. Then we're going to continue now simplifying radicals containing variables. So I'm going to give you time to do this work. We have plenty of time today to work a lot on radicals, and then we're going to continue after this. So when we have variables in the radicand, we're going to do the same thing. Sometimes we need to split the radicand into parts. One part is going to contain perfect squares, and the other part is going to contain the non-perfect squares. So when we have variables, we're going to pay a lot of attention to their exponents. So for example, so let's say this is a variable and this is the exponent. So there are only two possibilities. Either n is odd or n is even. So I'm going to show you how to rewrite a variable as a perfect square when the exponent is even. So when the exponent is even, you're going to write this x to the n. So let's say that you are taking the square root of x to the n. You're going to rewrite this radicand as x, and you're going to divide the exponent by 2, and then you're going to square this expression, and then you're going to still have your radical sign. So this is what you're going to do when n is even. You divide the exponent by 2, so you're going to get an integer because n is even. So if, for example, if n is 4, then 4 divided by 2 is going to be 2. So let me give you an example. If you have x to the 4, then you're going to divide the exponent by 2. I'm going to write this here first. You're going to square the thing, and you're going to write your radical. And at the end, you're going to simplify this, so you're going to get x to the 4 square. So now this x to the 4 is written as a perfect square. So let's say that you have x to the 20. It's another even exponent. So x to the 20 can be written as x to the 20 divided by 2, and then you square the thing. So if you do that, you're gonna get x to the 10 square root. The next steps, you know what to do in this case. So you can cancel radical with exponent, radical with exponent. So that's the purpose of rewriting a variable as a perfect square. But this is when your variable has an even exponent. Now, what happens when you have n as an odd exponent? So when you have that, you're going to rewrite your variable. So I'm going to again write x to the n now. But this time, n is an odd number. So you're going to write this as x to the n minus 1 times x. So we do this because if this is an odd number, then n minus 1 is going to be an even number. And if you have here x to an even number, then you know how to do. You're going to do all these steps. So in other words, you're going to get x to the n minus 1 times the square root of x. And then you proceed this is now an even number, n minus 1, then you're going to do all these steps. So for example, if you have x to the 7, and you're going to take the square root, x to the 7, in this case 7 is an odd number, so you cannot divide 7 by 2 like in these cases. So in this case you're going to subtract 1 from 7, so you're going to write x to the 6 times x. Then you're going to be able to break this into parts. Now you're going to see why I mentioned before. You're going to have a radical with perfect squares and another radical with non-perfect squares. Then the next step is you need to rewrite this as a perfect square by following this rule. So I'm going to solve 3 problems, and then you're going to continue doing the same thing, and that is going to be all for today. So let me solve 3 problems. So we're going to have plenty of time for your questions after the lecture ends. So we're going to solve example 3. Example 3 on page 581. So we're going to simplify the square root of 72 times x to the 14. So you're going to work coefficients and you're going to work variables in different paths. So for example, first I need to break 72 into factors, one of those factors to be a perfect square if possible. If not, this 72 goes into the radical sign with non-perfect squares. But in this case, 72 can be written as 36 times 2. So that's 72. So I can have now radicals here. So this is my radicals, my radicals, my radical sign containing the coefficient split in 2 parts, and now x to the 14. 14 is an even number, so x to the 14, I'm going to leave x to the 14 in this way because this is a perfect square. This is a perfect square. So any variable raised to an even power is a perfect square. Then I have this 36 is a perfect square. And then I have this number 2, which is a non-perfect square. So now I can break this into radicals. One radical is going to be for perfect squares and the other radical for non-perfect squares. The only thing that is not a perfect square is the number 2. So that goes there. So remember, this is the radical for non-perfect squares. Now the radical for perfect squares, I have 36, which is 6 to the second power, and I have x to the 14, which is x, 14 divided by 2 is 7, and this is to the second power. So this is just the rule that I just showed you before. So now you have the first radical containing perfect squares, okay, and the radical containing non-perfect squares. So let's finish the problem. This can be split into radicals to see very well how we're going to cancel everything. So that's my first perfect square. Then I have another perfect square, which is x to the 7 square, and then I have square root of 2. So you can see the reason of writing everything as perfect square, because in that way we're going to prevent from making mistakes. So I'm going to cancel this exponent with this radical, this exponent with this radical, and that's it. I don't have another exponent here to cancel with this other radical. So look at the radicand carefully. So you can see here that you have only 6. That's the only thing that is left once you remove the exponent and the radical. Then you have here, and this is a product, and you have x to the 7. That's what is inside of the parentheses. because the exponent was removed at the same time that we remove a sign, and then we have this radical sign that is untouchable because we cannot do anything else with that radical. So that is going to be the answer for this problem. 6 times x to the 7 square root of 2. Okay, 2 more examples. So you're going to need to practice this very, very well, because in that way you're going to be able to solve equations that contain radicals and do another operations involving radicals. So now I have example 4. It's another simplification. So we're going to simplify. Square root of 50 x to the 7. So again, we're going to check first the coefficient. Can I write 50 as a perfect square times a non-perfect square? Yeah, I can write 50 as 25 times 2. Okay, that's the first part. Now, is x to the 7 a perfect square? No. Now I have an odd exponent, so I'm going to write this as x to the 6. I'm going to decrease in 1 times x. So now I have what I need, because this is a perfect square and this is another perfect square. So these are the perfect squares. The rest is not, the rest are non-perfect squares. So I'm going to have one radical sign for my perfect squares. So I'm going to start with 25. 25 is 5 to the second power. Then I have another radical for the other perfect square. So it's x to the 6. I'm going to write x to the 6 as x to the third, because 6 divided by 2 is going to be 3, and then you square it. So now x to the 6 is written as a perfect square. So I have two perfect squares, so I have two radicals containing perfect squares. Now the last radical, I only need one radical for non-perfect squares, because you cannot simplify further. So what is remaining from this radical is this number 2 and this x. So I only need one radical for non-perfect squares, only one. One radical only for non-perfect squares, and you can have as many radicals. You can have radicals as many perfect squares you have. So in this case, I have one radical per each perfect square. So that's my technique. It's not in the book, but it's something that has worked for me a long time, for a long time. So let's finish this. So you can see here that you can cancel this exponent and this radical, this exponent and this radical. So look at the radicands carefully. You're going to see that the only thing that is remaining from this cancellation is just 5. From here, the only thing that remains is x to the third power. It's inside of the parentheses. And finally, the square root of 2x. So that is going to be the final answer for this problem. So we have one more problem, and then it's going to be your turn to work on these procedures. So let me write example 5. So let's see, example 5. Example 5 on page 582. We're gonna multiply and then simplify. So multiply and then simplify. So we have the square root of 6x to the 8 that multiplies 2 times x to the third. So now you're gonna see the importance of multiplying because if you treat these radicals independently, see that only this variable can be simplified because this is a perfect square, but this one, this coefficient cannot be broken into pieces because what are those two numbers, one of those being a perfect square that you can get from this from breaking 6, from factoring 6. There are no numbers. The same thing with number 2. And next to the third one, you know how to proceed in this case. You can just decrease in 1 the exponent, then you have a perfect square times x. But it's better to multiply first, so that's the recommendation. So we're going to multiply coefficients. So 6 times 2 is going to be 12, and x is going to be just the addition of the exponent, so it's going to be to the 11, x to the 11. So now we're going to simplify this radical, and by simplifying we mean that we need to break the radical into radicals. Remember, one is for perfect squares and the other radical is going to be for non-perfect squares. So 12. So I need to factor 12 in two factors. One being a perfect square, so you know that 4 times 3 is gonna work for us because 4 is perfect, it's a perfect square, 3 is not, but that's what I need. Then x to the 11 is going to be written as 11 minus 1 is 10 times x. Remember, anytime that you subtract 1 from an odd exponent, then you get a perfect square, and then you just multiply by x. So because in this case x to the 10 times x is x to the 11. So now I have 4, is a perfect square. I have 10, this is another perfect square. So I have 2 perfect squares, and the rest are non-perfect squares. So let's start. 4 can be written as 2 square, and then I have my radical sign for the first radical, for the first perfect square. Then I have x to the 10, so it can be written as x to the 5, because 10 divided by 2 is 5 square. So that's the second radical containing a perfect square, and then just a single radical for non-perfect square. So I have 3 here, and I have x. So again, I have my last radical is for non-perfect squares, and the other radicals preceding this one are for perfect squares. So let's finish our work. You can see here that you can cancel this exponent with this radical, this exponent with this radical. So don't forget removing the radicals anytime that you remove a exponent. So we're gonna finish with 2 from here. That's the only thing that is remaining, the thing that is inside, the number that is inside the parentheses. Then I have x to the 5th power. Then I have the radical for non-perfect perfect squares. So I have 3x here. So that should be the answer for the last problem. So now you're gonna have the opportunity to work on this. No, we have one more problem. I found one more problem involving fractions. So this is example 6 from page 582. So the first one is the square root of 100 over 9. So in this case, you can just break this into radicals, the square root of 100 and the square root of 9. And then you see that you have a perfect square here. This is 10 square over 3 square. Then you can cancel radicals and exponents. So you end up with 10 over 3 for this first problem. Then we have the square root of 40x to the cube over the square root of 6x. So in this case, it would be better to combine these two radicals in a single one, into a single one. So I'm going to get 48 over 6. That's the division of the coefficients, and then I have x cubed over x is going to be x squared, and 48 over 6 is going to be 8 x squared. So we only need to simplify this part, so we need to break the coefficient. This is already a perfect square, so we only need to break 8. 8 is going to be 4 times 2, then I have x squared. So again, this is a perfect square, this is a perfect square, so these are my perfect squares. So I have one radical for 4, that is 2 squared, and then I have another radical for x squared, and then I have a radical for the only non-perfect square, which is 2. So then you can cancel exponents and radicals. So if you do that, you can remove this and this, you can remove this and this. So what remains is 2 from here, x from here, and the square root of 2. So that's the final answer for this problem. So now it's going to be your turn to work problems now from the same exercise set as before. So we have 8.2 exercise set on page 585. So let's see. You're gonna simplify. You're gonna simplify first. So we have problem 30 is the square root of 36x squared. Then we have let's see. You have 50 is the square root of 49x to the 5th power. Then I have 52 is the square root of 12x to the 7. Then you're gonna work now. We're gonna multiply and simplify. Multiply and simplify if possible. So we have 58 is the square root of ax times the square root of 10y. Then we have 60 is the square root of 20x times the square root of 5x. Then we have 62 is the square root of 2x squared multiplying the square root of 10x. And then we have 64. 64 is just the square root of 50x to the 9 multiplying the square root of 4x to the 4. And finally 60, no, let's see, you're gonna work 88. 88. That's the last one. 88 is the square root of 75 x cubed over the square root of 3x. So those are your problems. You're going to solve those problems and you're going to send your solutions by using the chat box or by submitting your PDF files by using the corresponding assignment in Canvas, on Canvas.